Good evening, Professor, and thank you for being here today. My name is Harshavardhan, and I'm excited to present my project titled Improving Healthcare Predictions with Random Forest and Spark ML Library. This project was carried out using the Apache Spark ML library, and it aims to use the machine learning to aid early detection of the heart diseases. So let's dive into why this problem is important. So this is the agenda for today. I'm going to cover each and every aspect of that. So it is interesting, it's a interesting fact to know that cardiovascular disease is leading cause of death worldwide, accounting for approximately 18 million deaths each year. Early detection is crucial as it can literally save lives. So traditional diagnostic methods may not always scale or adapt to these massive data sets. That is where the machine learning steps in. So, by training the predictive models on a patient data, we can help identify risks early and more accurately. To handle this efficiently, we leverage the Apache Spark, which is a big data processing framework, which allows us to build scalable distributed machine learning pipelines. So, the core research problem we wanted to solve is, can a machine learning model predict the heart disease effectively? So more specifically, I can keep it like, will a random forest model perform better than a standalone decision tree when trained on a same data set? Our conjecture is that ensemble methods like random forests will outperform the single tree models because they reduce the overfitting and improve generalization, especially on the complex data sets. So, a number of studies have been number of studies have used the machine learning for heart disease prediction, applying models such as logistic regression, naive Bayes, and SVM. However, many lack the scalability, and few explore the ensemble models in depth. Some also fail to utilize the distributed frameworks like Apache Spark. Our work addresses these gaps by implementing both decision tree and random forests using the Spark ML library, enabling scalable training and evaluation across the large data sets. So coming to the methodology, we have used the UCI heart disease dataset obtained from the Kaggle website, which includes 303 records and 14 features like age, sex, cholesterol, chest pain type, etc. Our goal was to perform binary classification, predicting whether a patient has a heart disease or not. The project was built using PySpark and Spark ML library to take advantage of the pipeline based machine learning. So the data processing is a critical step. We removed missing values and transformed the target variable into a binary form. For example, 0 is for no disease and 1 is for the presence of a disease. And the categorical features like sex and chest pain type were encoded using the string indexer and one hot encoder. We use the vector assembler to combine features and the standard scalar to normalize the numerical values using the z-score normalization. This standardization ensured that all features contributed equally during the training. So for the decision tree model, we used a simple configuration with limited depth to serve as our baseline. The random forest model, however, was tuned using a parameter grid. We varied the number of trees, max depth, feature subset strategies, and minimum instances per node. We even used a threefold cross validation to select the best model. When finally the data was split into an 80-20 combination of training and testing sets. So this is the flow chart for a better understanding and what was the process followed throughout the project. And we can see here that the tools I have used for the experiment for the project was PySpark, Python, and Matplotlib. Matplotlib was used for plotting some graphs in the end to compare the results for the decision tree and the random forest models. The data was split into 80-20 combination, and the results were compared on these four metrics: accuracy, precision, recall, and F1 score. So we can see the model performance comparison here for each and every metric. for the decision tree as well as the random forest. So the results clearly support our hypothesis. The decision tree achieved an 80.89% accuracy with an F1 score of 81.12%. The random forest model outperformed it with 85.11% accuracy and F1 score of 85.21. These results highlight the benefit of using ensemble methods. Feature importance analysis revealed that chest pain type, thalassemia, and age were the most influential features in the prediction. In conclusion, our work shows that the random forest models provide a better performance than the decision trees in the heart disease prediction. Spark ML Libraries Pipeline API allowed us to construct scalable, modular machine learning workflows. Our conjecture was validated, and the system we built is accurate, scalable, and interpretable. Looking ahead, we can implement the gradient boosted trees for the further improvement of accuracy. Real time predictions using the Flask or the Spark streaming are also on the roadmap. Integrating with electronic health record systems could enable the real world deployment, and also we also want to perform, we can perform the fairness checks and tests the model on more diverse data sets to ensure unbiased results. So finally, I would like to thank Dr. Ferosh for his guidance and everything in completing this project. Thank you so much, Professor. And these are the few references which I have used to complete my project. That's it. Thank you, sir. Thank you, Professor. Thank you.